this is all going according to plan. You're going to be watching this video at the beginning of term 3. And I really hope we are back into a little bit more normal time. But as I'm recording this, this is still the end of term 2, so I don't really know. I hope you have a lovely, lovely holiday, and you're nice and refreshed, and you're ready to finish the year. And I wish us all a really happy and a bit more normal year. Anyway, we're doing quite well. Just to let you know, we're doing quite well with this whole program of AP. We're still a bit ahead of the game. We just need to finish integration, which will take us 2-3 lessons maximum. And then we are moving on to our optional module, which is going to be easier and quicker. Okay? So we're doing really well. Now, what I'm going to do in this series of lessons, it's called Riemann sums. We're going to learn how to calculate Riemann sum. But really the aim here is to prove that what I told you last lesson was true. What did I tell you? I said if you want to find out the area under a curve, if you want to find the area between the curve and the x-axis, what you're going to do is calculate the definite integral between the two vertical lines. That's kind of limits your area. So I'm saying we're going to prove it. We're going to kind of prove it. I will give a full proof, but that's beyond what you need to know in the syllabus. So that will be an optional video. But we are going to show that it is. Let's put it this way. So starting with the simple case, and this is often the case in maths and physics. We start with a very simplified proof, or a simplified case to show that it's true, and then we work more complicated stuff. So we've got a linear line. It's always easy to work with linear lines. Y equal minus k minus x plus 2. And we want to find out the area between these two vertical lines. We're always going to choose vertical lines. If you're not choosing a vertical line, that's going to be more difficult. Okay? It can be done, but we're not going to do it. So choosing two vertical lines, and I want to find the area between minus 1, x minus 1, and x equal 1, and the curve. Okay? So if we take my advice, my instruction from last time, we know that that area is going to be equal to the definite integral, okay, of the function minus x plus 2 dx, and then I put the limits, okay, the little boundary, so it's from minus 1 to 1. Okay? And then we know how to do that, okay, so we're going to find the integral of each one part of this function. Okay, it's going to be minus x squared divided by 2, right? So the 2, when I do the derivative, we're doing the antiderivative, right? We're doing applying the antiderivative operator on minus x plus 2, meaning we're looking for a function. If we do the derivative, we'll get back to minus x plus 2. So that's going to be the first part. That's going to be the second part. Okay, I'm putting in the box, writing minus 1 and 1. And remembering that I don't need to add the constant. Remember, if I add that plus c, which happens when I do the antiderivative, but when I'm substituting these numbers, the constant will kill each other, commit suicide, so we don't need that constant. And now I just substitute 1 and minus 1, okay? So it's going to be minus 1 squared divided by 2 plus 2 times 1 minus, and I'm going to put that in brackets. Now substitute minus 1 instead of the x. So it's going to be minus 1 squared. I'm going to be careful, there's a whole bunch of minuses here, okay? Divided by 2 plus 2 times minus 1. I'm getting, this is minus half plus 2 minus, okay? Right, so this minus goes away, but I'm still left with this minus, so it's minus half minus 2. Okay, so I've got 3 halves, right? 2 minus half is 3 half. Minus, what is minus half minus 2 is minus 5 halves, if I'm not mistaken, right? It's minus 2 and a half, so which is minus 5 halves, but I've got minus 5 halves, so plus 5 halves, okay? And what I'm getting is 8 over 2, I'm getting 4, whatever it is, 70 square, meter square, whatever, okay? I hope I've got it right, okay? I'll just pause just to make sure. Okay, all seems to be right. Now, so this is what this way told me to find the area. But now I know a little basic geometry. Okay, I know this is a trapeze, and I know how to find the area here. Okay, I just need to do that base, okay, plus that base, okay, divided by 2 times the height. Okay, so what is that base? Well, all I'm going to do is substitute x equal minus 1 into that formula to find the y value. So I'm going to put minus 1 or minus 1, okay, because I've got to substitute minus 1 or minus 1, so minus 1 plus 2, and I'm getting 3. So this base is 3, right? That's the y value. I've got to do the same here. So now I'm going to substitute 1 here, okay? So minus 1 plus 2 is equal to 1. So this base is 1, okay? So I'm going to add the two bases, 3 plus 1. I'm going to divide by 2 because it's basically base plus base divided by 2 times the height. What is the height? The height is the distance between x equal minus 1 and 1, which is 2. Okay, so the answer is 4, and we got the same answer. So at least when it comes to a simple linear function, okay, it looks like I am allowed to use that rule to find the area by finding the definite integral for of a function. Okay, let's look at more general cases then. Okay, so our next step is to find, let's say, find the area underneath the curve of this quadratic function between x equals 0 and x equals 4. Now, here, okay, well, let's start with by finding out the area using the antiderivative. Okay, so I know that I can do it this way. I can say, I'm going to go from 0 to 4, and I'll put x squared minus 2x plus 2 dx. Okay, so we're going to do the antiderivative for each part of these functions. So it's going to be x cubed divided by 3 minus x squared plus 2x. Okay, and I'm putting the two limits, the boundaries, 0 and 4, and now I'm substituting 4 minus substitution of 0. So I'm going to get 4. 4 cubed is 64, is it? I think so. 64 divided by 3 minus 16 plus 8, okay, minus, look, I put 0 instead of all the x's, it's just going to be 0, okay? So hopefully, you're just going to have to believe me, or just believe what the book said. We got 13 and a third newtons, okay? Now the question is, how can I prove that, okay? Well, I can't really, because this shape, I don't know how to find the area of this curvy shape. And this is where this very clever dude, Riemann, came. He was looking into that, okay? He was looking, he's the one who actually discovered that, I guess, or he helped discover the idea of the integral. So how did he get there? He was thinking, how can I find the area of this shape? Okay? And he didn't know about integral. So what he said, look, what I can do, I can just divide this area between 0 and 4. I'm going to say like 1, 2, 3, and 4. And what I'm going to do, I'm going to create these blocks. Okay? I'm going to create these blocks, okay, where the blocks, okay, have the value of the function. Okay? I'm not really drawing it really well. Just a second. So this block, the value will be of the function here, 1. Alright? Yeah. And then the block here, okay, the block here, okay, the second block will be the value of the function at 2. I'm just going to pause, make it tidy up a bit. Okay, so this is what Riemann did. He started by dividing, okay, this area into 4 blocks. Okay? And he said, look, I don't know how to calculate the area under the blue curve. What I do know is calculate the area of these 4 blocks. Okay? How would we do that? Okay, well, the width of each block, okay, the width of each block is just 1. Okay, we're not working with units, we're not centimeter, it doesn't matter. Okay? It's just 1. 0 to 1, 1 to 2, 2 to 3, 3 to 4, the width is 1. What is the height? Okay? Well, the height changes. Each block has different height. What will be the height of the first block? Okay, the height of the first block is basically, let me just write it, okay? It's the value of the function when x equal 1, right? It's f of 1, right? That's 1, that's x equal 1. This is f of 1, okay? What's the height of the second block? It's f2. height of the function at 2. Okay? And then, therefore, that will be, the height here will be f of 3, and here it will be f of 4. Okay? So we found the width of each block. It's the same. And that's a very crucial part. All the widths are the same. The height is different. The height is the value of the function on the right edge of that block. Now, what will be the total area? Okay, what will be the total area? It will simply be the sum of the area of each block. Okay, so I can write it down as, okay, the width, okay, width time f1 plus the width of the second block time f2, and then for the rest, okay, time f3 plus 1 time f4. Okay, so what I'm really doing, I'm summing up the values of the function. Okay, now if you do that, okay, let's just find out what it is. What is f1? Okay, I need to put 1 here. So it's going to be 1 squared, okay, minus 2, which is minus 1, plus 2 is 1. Okay, I'm just substituting 1 here. So 1 squared is 1, minus 2 is minus 1, plus 1 is 1. What is f2? Okay, 2 squared is 4, 4 minus 4 is 0, 2. Okay, 3 squared. 3 squared is 9. 9 minus 6 is 3. 3 plus 2 is 5. Okay, just checking that I've got it right, yeah. And last one, 4. 4 squared is 16. 16 minus 8 is 8. 8 plus 2 is 10. Am I getting it right? Yeah, and apparently if you do that sum, the book says we're getting 18. Okay? So, what are we noticing? The numbers are not the same. Okay? Now, I think you can very clearly see that this is not an accurate way to find the area, isn't it? Okay, what's the problem? Okay, look, what I'm calculating, I'm not calculating the area of I'm not calculating the area under the curve, I'm calculating the area of these blocks. And that's obviously not the same. I've got this extra bit here and here a little less. So it's not going to be the same. But it's a starting point. Because what are we going to do now? How can I get a better estimate of the area under the curve? And I think a lot of you would have answered me. You will realize that you need to make the blocks more narrow. So I'm still going from 0 to 4, but instead of a width of 1, maybe I can do a width of half, or maybe 0.1, or maybe 0.0001. The smaller, the narrower the block are, the more blocks we're going to have as well. Okay, so it will be a more complicated calculation. But the thinner the blocks, the more of them, the more accurate estimate we'll have of that area. Okay, right, we're going to carry on from here. Okay, so what I've done, I followed my own advice and I said, right, we've got a curve. Now it's a general curve, so I don't know anything about that function. It's just a function, okay? I want to create some kind of formula that doesn't depend what function it is. So we'll just give it a general function f. And I want to find out the area between these two lines, x equal a and x equal b. And this time, because I want to have something a bit more accurate, I divided lots of these blocks. Okay? I've actually used n blocks, again, because I want a general formula, so I divide it into n blocks. And obviously, the larger n is, the more accurate I'm going to get the area. Okay? So yeah, I've divided to n blocks, starting with block number 1, x1, then x2, x3, x4. So this is the values of x. Okay? Obviously, the first one will be higher than a. Okay? It will be, if this is a, a plus something, and every time I'm adding more and more and more. Okay? And then eventually, ultimately, the last block will be where x equal b. Okay? Right? It will be over here. That's the nth block, xn. Now, first of all, I want to find out what's the width of the block. In the last example, okay, the width of all the block was the same, and it was equal 1. Okay, so obviously here the blocks also have the same width, but the value is not going to be 1, it's going to be smaller. What is it going to be equal? Well, think about it. What's the distance between the first and the first left edge of the block and the right edge of the last block? It's going to be b minus a. Okay? So the width is not going to be obviously b minus a. It's going to be b minus a divided by the number of blocks. Okay? How many blocks do I have? N. Okay? So let me just write it down here. So the width of the block is going to be B minus A divided N. All that area, or all that length, divided by number of blocks that I have, N. Okay? And as you can see, the more blocks I have, the higher N, the narrower they're going to be. Okay, now I want to find out a formula to find out the value of X. Okay, the value of X, how much is it? Okay? So the first one will be, the first one must be A, isn't it? No, not going to be A, it's going to be a little bit more than A. Okay? Because if A is X equal A here, X1 is a little bit more than A. Let's actually find out what is it going to be. Okay? So before we get the formula for the A for a certain value of X here, let's find out what is X1 equal. Well, X1 is going to be equal to A, okay, plus the width of the block. What is the width of the block there? So it's going to be A plus B minus A. B minus A divided by A. Okay? Now, X2. What will be the value of X at X2? X2 is just a name, but what is actually X equal to? Well, again, it's going to start from A. Well, it's going to be X, the value of X1 plus the width. Okay? Another width of the block. So it's going to be A plus B minus A over N. Again, plus B minus A over N. So in other words, I'm adding the width of the block twice. So obviously, I don't need to write down like that. I'm just going to write 2 times. Okay? Now, hopefully you see where I'm going for. If I want to find out the ith, the seventh, the nth, I want to get the formula for a general X here. Well, it's simply going to be A plus the index. I is the index. Okay, so for the first one, it was just 1. For the second one, it will be 2. For the third, obviously, it will be 3 times that. So for the I block, I don't know how to say ith. Can you say ith? And the ith block is going to be I times B minus A over N. Okay? Now, just to check here that we are right, let's just find out what is the nth block. The nth block is the last block. That needs to be equal to B, right? Okay? The X over here is equal to B. So let's see if that works, okay? So I'm going to use that formula, A plus I. What is I equal to? What's the index? Well, now it's N. Okay? So it's going to be N times B minus A over N. But check what happens here. The N cancel out. Okay? So I've got A plus B minus A, which is indeed B, as it should be. Okay? So this is really, all that stuff was just to generate this formula. That's what I was trying to do here. Okay? The value of X, okay, is going to be equal to A plus I, B minus A over N, where N is the number of the blocks. A and B are the borders of this graph. Now, why am I doing this? Okay? Why? I'm doing it because just as I did in the example before, I'm going to try and find out a formula to calculate the area of this. This is called the Riemann sum. Okay? We're adding the area of this block plus the area of this block plus the area of this block. Okay? So it's going to be an estimate, not accurate, but an estimate for the area under the curve. Okay? So why did I need to find out the X value here? Because ultimately, okay, how do I find the area of this whole thing? I need the area of each block. How do I calculate the area of each block? Well, the first thing I need is the width. And the width is the easy bit, okay? That's the width, okay? And it's always the same. What's a bit more difficult is to find out the height, okay? The height of each block changes. You can see it increases here. What is the height? The height is the Y value at that specific X. So I've got the formula, okay, general formula, but I need to have some kind of formula to find out what's the X at this specific point. So now I've got it. So now I'm going to find out, I don't know if I can write, yeah, I'll write it here. I'm going to find f of X of I. And just write, I want to just write it the same as these guys did it. I'll just pause for a second. Right, so the formula that I have, this is the formula for the X. The formula for the Y value, which is really the height, okay? This is the height of the block, okay? This this is the width of the block, that's going to be the height of the block, is f of a plus I b minus a over n. Okay? Now, there's nothing else I can do now because I don't know what function I'm dealing with. Is it quadratic, is it linear, is it exponential, is it trig? Okay, I don't know, but this is all I have. I have the width and I've got the height. So if I want to find out the area, okay, what I'm going to do is the area of each block. In other words, b minus a over n time the height. That's the width time the height. Time f of x1. That's the height of the first block. Then I'm going to do plus b minus a over n, which is the width of the second block, time f x2. Carry on, carry on, carry on, carry on for 3, for the third, for the fourth, for all the blocks until I reach my last block, where again the width is the same width, time block n. Okay? So that's the formula for the area. Now you can see I've got lots of little sum, lots of terms in that sum. One of the things that I'm sure you've already noticed, okay, is that all the width are the same. So if all the width are the same, then I can get them as a factor out, okay? So I can write down the area as b minus a over n time, okay, fx1 plus fx2 plus all the way to the last value, which is xn. Okay? Now, you know, there is a way of shortcutting this little bit. Obviously, there's brackets here. Okay? Instead of writing fx1 plus fx2 plus all that stuff, there is a certain notation which I think you came across that before, and that sigma. Okay? Sigma means sum of. Okay? So I'm going to write that one more time. Okay? I'm going to write b minus a over n times sigma if xi. So this sigma tells me to sum all the values, or the y values, the fxi of all the x's here. So when I write a sigma, I need to write, the I is the index, so I need to write down what is the index running from. So the first index, the first I is 1, so I equal 1. We write that at the bottom. And then above the sigma sign, I write what's the last value of I. The last value of I is n. So I runs from 1 to n. And that is the formula that I work with, and this is what we call a Riemann sum. Okay, let me just make sure I wrote it nicely. Great. Okay, so all I can should be, okay, this is the width, okay, which is constant. This is the first value of I, 1, the last value, and here I've got all the values of the function. And I'll just repeat once again that this is the estimated area, not the area, it's the estimated area, and it's not accurate. To make it closer and closer and closer to the true area, what do I need to do to n? I need to make n bigger. If I want to make it super accurate, what do you reckon we need to make n approach? What should be the limit of n? I'm kind of going ahead of myself, but I think some of you already figure out. If I want to make that true formula for the area, then n must approach infinity. Okay? In other words, I'm going to have infinite number of columns, okay? And the width of each one of these columns, if n is infinity, b and a are definitely finite, so finite divided infinite will be 0. So you see we're heading back into calculus territory. But I'm not going to get into that calculus. I'm going to stop the video here. In our next video, we're going to use this formula to solve a few examples. Okay, see you then.